Our project analyzes and applies the findings from an experiment done by our advisor, Dr. Rao, and his team, titled The Impact of Low-Cost Dilute Surfactants on Wettability and Relative Permeability. We will be applying these results from this project to a reservoir scale simulation. In this experiment, Dr. Rao and his team tested 3 different core samples from the Yates field in Texas. These cores were flooded using low-cost surfactants at dilute concentrations at both ambient and reservoir conditions. The goal was to study how oil recovery rates were affected and to optimize the most cost-efficient concentration that was used. The experimental data shows that the recovery rates of oil can be significantly increased when surfactants have been introduced during the water flooding process. We will attempt to simulate this experiment on a reservoir scale, including reservoir conditions. This will help determine more accurate effects that it has on the oil recovery rate. Since the last time we presented, we have focused on educating ourselves more on our topic, particularly the effects of surfactants on wettability and relative permeability, and have also familiarized ourselves with the software that we will be using for our simulations. The software is CMG. Jacob and Ali will be explaining briefly what we have learned and how it applies to our project.
So for our senior project, we'll be simulating surfactant injection on a reservoir scale. But what are surfactants? Surfactants are polar compounds that have conventionally been used to reduce oil-water interfacial surface tension, which improves recovery during water flooding. They have a hydrophilic head and a hydrophobic tail. This allows the head to dissolve in the water phase while the tail remains largely out of the bulk of it. A familiar example of surfactants is the use of soap to reduce water surface tension when you're cleaning something. There are 3 types of surfactants: cationic, anionic, and non-ionic. However, for oil recovery, it's primarily anionic and non-ionic that are used. Anionic are the most commonly used ones. They have a negative charge on the hydrophilic head, which assists in reducing interfacial surface tension. Non-ionic are polar, but they have no charge on the hydrophilic end, which allows them to effectively emulsify oil and water. Non-ionic are also less sensitive to contaminants such as salinity in a solution. The primary means to quantify surfactant use and its efficiency is the capillary number. This describes the ratio of capillary to viscous forces in a fluid flowing medium. Today in the industry, most surfactant use focuses on reducing interfacial surface tension. The effects that surfactants can have on the contact angle in an initially oil-wet reservoir have been often overlooked. This is due to a false assumption that all reservoirs are strongly water-wet. The wettability of a reservoir can be defined by the oil-water contact angle, 0 meaning strongly water-wet and 180 being strongly oil-wet. The use of surfactants to induce intermediate wettability, a contact angle close to 90, results in a very large capillary number, meaning that the viscous forces will dominate the fluid flow. This reduces trapping and significantly improves oil recovery. We plan to simulate non-ionic and anionic surfactant injection using Dr. Rao's lab experiment and data as a precedent. From our simulation, we will be able to determine whether or not surfactant-induced wettability alteration is feasible in a particular field at reservoir conditions and on a reservoir scale.
CMG is going to be our main software package to use to model the experimental results we have for our project. As the main idea for our project is to alter rootability. So first, we will simulate the lab results that we have and to see if we will get the same results that we got from the experimental work. Then we can upscale that model into a reservoir. CMG is going to be our main software package to use to model the experimental results that we have for our project. So as the main idea or the main goal of our project is to change the wettability, to alter the wettability. And this will be done by introducing surfactants. And the way we are going to simulate the surfactants in the model is by changing the relative permeabilities that we have from the experimental work. After creating the model, we will test it, and if we will get the same results that the experimental work got, we have been practicing CMG for the past 2 weeks, and thanks to grad students from our department, they have been a great help to us. We were able to come up with this geometric representation of our core, and this is we will continue practicing and entering the data we have from the experimental work. So after we create this model, we will introduce the surfactants by changing the relative permeabilities, and we will match the results we will get from here to the results we have from the experimental work. So after we match the results, we will upscale this model dimensions into a reservoir scale that can be used in the industry.
This is a general timeline of our project for the fall 2016 semester. In red are some of our goals that we have completed throughout the semester. In green are the goals that we have started and are still continuing to work on. And the two black goals at the end are our final presentation, our project proposal, which we'll be working on in the next few weeks. Concluding the semester and during the Christmas break, we will be working on performing some more thorough simulations of our base case with our core samples and trying to match those results to the experimental results that we have. And then once we can do that, we will begin trying to scale up our results on a reservoir scale.